Welcome back to Multigrid Methods. We're finishing today with Chapter 8. In fact, we won't be too long into the slides before we're completely done with this chapter. The basic concept that we want to talk about for um, this final class in Chapter 7 is these generic smoothers for the 2D cell-centered finite difference method. We talked about prolongation. We talked about restriction. If we define the stiffness matrix, then the only thing really that's left is the how you do the smoother. And so I want to address this from a not very theoretical level. What I mean by that is we're not going to discuss the theoretical concepts. We're just going to discuss basically manipulations and numerical recipes and things that work and maybe some things that don't. And then we'll get into some code and we'll show how and maybe why things work and what works well, etc. So we're fairly deep into this last section, and I think we're probably somewhere around here. And back up. Okay, so we're talking about cell-centered smoothers for the 2D setting where we have non-constant diffusivity. And that means we're working with a fairly complicated finite difference operator, and we want to come up with some sort of smoothing strategy. So I've got two to talk about. The first is called the quasi-Jacobi smoother, or damped, uh, actually more specifically, the damped quasi-Jacobi smoother, and then the damped quasi-Gauss-Seidel smoother. So to keep the discussion general, as I said, we're going to talk about the non-constant diffusivity case. And so what we do in smoothing in 2D is the following sort of picture. We've got a grid. Remember, smoothing is just a general linear iterative scheme that we're doing to on a certain level or to a certain level. And for the Jacobi method, we basically got to update all of the values of our grid function at every grid point. So here are here's our grid of points. And by grid values, I mean there's a grid function defined on those cell-centered points. And it has a certain values, and we've got to update those if this is a 4x4 grid at all 16 points. Now, what makes life a little bit easier is if we supplement this by having the ghost cells out here. So in addition to these 16 interior points, of course, there are 16 ghost cells, and those have or could have values at them. It turns out it makes life easier if we think about having values there and enforcing the homogeneous Dirichlet boundary conditions. So what we're going to do is suppose I have a grid function defined for some step sigma. We want to update this via smoothing to sigma plus 1. So how can we do that? Well, first of all, let's suppose that this grid function is only an interior grid function. It's only got values defined on these interior cells, okay? Well, if that's true, it's very easy to extend that by adding on the ghost cell values in such a way as to satisfy the homogeneous Dirichlet boundary conditions at the discrete level. So we just extend that function a little bit. That means if we have a value here, we're just going to say at this point, it's minus that value. And if we have a value here, then at this point, it's minus that value, etc. So if we have this given, we can extend it to a function of this type. This means a cell-centered function, cell-centered grid function that has homogeneous Dirichlet boundary conditions. We'll use the same notation for both the given function and then that extension. Now, For the quasi-Jacobi smoother, what we do is we're going to write out the equations, okay, the approximation, and we kind of assume that write it out as if UL sigma is a true solution for your problem. It's not, right? It's just an iteration that we want to update. So write out your method as if that was a solution. And then where you see just the points ij, which will be these 4 points, we're going to replace that with this new grid function called ZL. And of course, it's defined at the point ij. So well, let's call that value at that point naturally ZLij or ZL at the point ij. So that means what we're doing is we're marching across this grid and we're going to update the values. But what we're actually doing is updating that grid function ZLij. Okay. So we've come in here, found any instance. We pretend that UL sigma satisfies the 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 finite difference method. It doesn't exactly because it's not a true solution. It's just an approximation that we want to update. And then we'll go in and replace that with Z, right? So that's the idea. Okay, every instance of that. So that defines a new grid function, ZL, that we're updating on this level L. And well, it'd be nice if I could just uh, come up with a calculation or solve for that ZL, right? That would make life easy. Well, this is for every fixed I and j, this is just an equation. We can solve for ZLij. And we discussed this last time. If I do this, if I solve for this, then ZLij is just what you see here. It's these two quotients. Now you can just treat it as a single quotient, but I couldn't write it on one line. And so I've broken it up into two fractions, right? So the denominator is the same. Okay, the denominator is this big ugly thing. And those were just that was the denominator is just the factor that was multiplying the ZLij whenever I pull out all of ZL, those common factors of ZLij. When I solve for it, I divide by it, etc. Okay, but in any case, I get an explicit formula for this update, this thing I'm calling ZLij. And the reason why this is called Jacobi or quasi-Jacobi is because basically I can view the point ZLij as being that one associated with the diagonal entry of my matrix. Okay, so I'm kind of extracting the diagonal, and this has the same effect of the process that you do in constructing the Jacobi smoother. You break the stiffness matrix into upper portion, diagonal portion, and the lower portion, etc. All right, now once I've got this ZLij defined for all the points ij, and notice that that just requires knowing what f is, and f is a given function. Everything over here on the left-hand side is given. That's the diffusion coefficient at some edge grid point, and this is the value of UL at I plus 1j at step sigma. So this is all known. That's known. That guy is known. That guy is known. Everything on the left hand or the right hand side is known. And it doesn't matter what order I do this update for ij because all of this stuff is already known. I can do it in any order that pleases me or that goes the fastest or whatever, most natural. So I can update this in any fashion I want. And this tells me that I can actually do this update actually in parallel, which is a nice feature of the Jacobi method. So it doesn't matter what order I compute the entries of this update function. Once I have it, then I'm going to compute the update. This is actually the thing I want to obtain as an update. I'm going to obtain that just by weighting ZL against the old value UL sigma, and I'm going to interpolate between those two values by choosing a damping parameter omega between 0 and 1. If I choose 0, which is not allowed actually in this case, then actually nothing happens. It's basically a boring situation. That says if omega is zero, then that's zero. This is one. And so basically you're saying that UL sigma plus one is just UL sigma. Nothing is happening. So that's useless case. If I take omega equals to one, then that's just the Jacobi method, or what actually is called the quasi-Jacobi method in this case. Well, what we can show is basically the situation is like what we've been encountering all along, and that is, you know, choosing omega between a half and two-thirds is going to give me good smoothing properties, actually. And so this is what we're going to try to prove with some experiments, hopefully. Now, there's no hard and fast theory for that because the hard and fast theory is really only something that can be established whenever I know what D is. And in fact, the best theory is for the D equals constant case. In that case, I can say what the best smoothing parameter is, or what the best damping parameter is for smoothing. But in this case, I really can't say. I don't know. We'll just have to do some experiments and see what proves to be the best. Okay, so why do we call it quasi-Jacobi? Well, it turns out that this whole method could be derived from the true Jacobi method, and it will be the same at all of the interior grid points. It's just that at the boundary grid points, the true Jacobi would require some sort of modification that I don't want to do because it's going to make my life a little bit harder. It turns out it's easier to use what I just showed you. Um, so in particular, one thing you'll see is that in the quasi-Jacobi, I'm always dividing by that same quotient. Now the quotient changes at each point I and j where I'm doing my update, but what I mean is the structure of the generic update is always the same for quasi-Jacobi, but in the true Jacobi method, this will change from point to point. In fact, it's the same in the interior, but near the grid point or near the boundary points and at the corner points, it's going to change. And so that's a hassle that I don't want to deal with, and it makes life easier to do it this way. But it's not exactly Jacobi, it's what's called quasi-Jacobi. Now, as I pointed out, well, I did because I didn't point it out, but as you know from the finite difference case that we discussed way back in earlier sections, what used to be called chapter 3 and is now going to be chapter 4, we showed that if you use omega equals 1, that's the standard Jacobi method or the standard quasi-Jacobi method in this case. And there's no damping, and the method doesn't adequately smooth high frequency errors, and therefore your multigrid method is going to fail to converge. But generally speaking, if I choose omega in this range of 1/2 to 2/3, you're going to get a pretty good multigrid convergence, and we're going to test this out with some examples. All right, let's move on. So what Jacobi does is a little bit wasteful in some sense, and that is I kind of am updating these point values at each grid point, but I'm not immediately using the updated values in the computation of the next value at the next grid point. And what the Gauss-Seidel method says to do is to, once you get an updated value at a grid point, when you calculate the update at the next grid point, use the new update that you just obtained from the previous one. So the setup is kind of the same. We're going to suppose that we're given a guess at sigma, right? At iteration sigma, and we want to update that to sigma plus 1. The first thing you want to do is create a unique homogeneous Dirichlet cell-centered grid function that is exactly the same as that previous one at the cell or at the interior points, but at the ghost points, this one, well, this one has ghost points in it, and it has the values of the ghost points set up so that the homogeneous, the discrete homogeneous Dirichlet boundary conditions hold. Okay. Now, now suppose that the indices are traversed in what we called forward lexicographic ordering. So basically, I have a grid of points, and actually, we're going to show this in a slightly future slide, I guess, but it's good to remind ourselves now. What does lexicographic ordering mean? It means if I've got a grid of, let's say, 4 rows by 4 columns, and I'm going to number it this way: 1, 2, 3, 4, 5, 6, 7, 8, etc. So when I come through here, I'm starting at this point. I'm updating that guy first, then I update this guy and this one. And so what I mean is when I'm updating point 7, I'm going to immediately use the updated value that I just obtained from point 6 in my updated calculation. And I'm going to also notice I've also updated all of these values. So I'm going to use all of those values if they come into my equation when I'm calculating point 7. Okay, let's go on further in our numbering. So we have 8, 9, 10, 11, 12, 13, 14, 15, and 16. So what I mean is what we have are updates, let's say up to point 7. I've already gotten 1. And actually, let's use a marker here. So I've already gotten 1, 2, 3, 4, 5, and 6. So I'm going to use those when I calculate point 7. But what I don't have are values at point 8, 9, 10, 11, at any of those points. So those are going to retain the old values. Now, when I'm doing this in the lexicographic ordering, you've got to remember that along this direction, you're counting I, and along this direction, J. So this point is I equals 1, J equals 1, I equals 2, J equals 2. This point is I equals 3, J equals 2, and so on, according to that lexicographic enumeration formula. But again, the setup is the same. We've got a grid function that has grid values at all 16 points plus ghost cells if we need them. And we're supposing that the indices are traversed in the forward lexicographic ordering. Then let's suppose we're at, say, point 7, which is going to be I equals 3, J equals 2, and we want to do the update. So the setup is the same. We're going to assume that, let's say, our function satisfies the equations, and then we're going to go back and put in the values according to whether they've already been updated and whether they're currently going to be updated. So I'm going to do this update at point 7. That's going to be my I and J point. Anywhere I see an I and J point, I'm going to put a dummy variable that I solve for, just like I did last time. Where points where I haven't visited yet, I'm going to use the old values of sigma. I don't have an updated value at this point. That's I plus 1j. That's here. That's point 8. And ij plus 1. Ij plus 1 is point 11 here. So I'm going to use the old values there. What about this guy here? I minus 1j. Well, I'm here at that point. I minus 1j is right there, 0.6. So 0.6, I'm going to use the updated value. And also 0.3, I'm going to use the updated value. That's ij minus 1 index. Okay. So that's how I set this problem up. It's different than Jacobi because I'm immediately using the updated values. And you can see if you know something about the standard Gauss-Seidel method, if you remember what we learned about it from the last semester, you'll see that this is entirely related to Gauss-Seidel as you apply it to solve a matrix vector problem, right? Okay, so that's all the variables where the unknown is this guy here at this point 7 that we want to find. And now this is called the damped Gauss-Seidel smoother. So you may have not, we haven't really talked about the damped Gauss-Seidel smoother yet, but as I said, it proceeds a lot like the damped Jacobi smoother. We first update this point here, which I was calling Z before, but now I'm going to call alpha. So I want to solve for that alpha. You can see everything is now known except for that guy. And I can just solve for it the way I did before. The denominator is the same as we had for the Jacobi case. It's just now, if I look across here in the values that I'm using in my formula, some of them are not updated yet, and some of them are updated because of the sigma plus 1. So not updated, but updated. Now, what we do is we calculate this guy, and before we move on to the next index in the forward lexicographic ordering, that is, before we move from point 7 to point 8, let us update this value using that a sort of interpolation like we did with the damped Jacobi method. We're going to interpolate between the value that we just found and the value that we previously had. And we're keeping in mind, if I use omega equals 1, then that's not really an update at all, and that's a useless method. If I use omega equals 1, then that gives me back the standard Gauss-Seidel method. And if I use omega between 0 and 1, in fact, I can even take omega bigger than 1, it turns out. And that's going to give me what's called overdamping. I didn't really discuss it, but that is a possibility. If I use omega bigger than 1, that's overdamping. That's a possibility. So in any case, whatever I choose to use, as long as it's sensible and it's converging, this is giving me an updated value. And now the idea in Gauss-Seidel is now when I move on to this next point, point 8, I'm going to use that updated value in the calculation for 8. So in the forward Gauss-Seidel framework, as soon as an updated value is obtained at some point ij, we're going to use it in the calculation of the next, or any of the next points, that is I prime j prime, the grid point I prime j prime, where I prime j prime has a forward lexicographic index which is bigger than the current one. So this just means all the future values are going to have the ability to use this updated value. Again, the name quasi Gauss-Seidel is used because we're not going to modify the stencil near the boundary and the corner cells as we would do in the true Gauss-Seidel. We're simply going to stick with this simple formula, and that gives us
I
what's
have
called
a question.
quasi Gauss-Seidel.
Uh,
Is there a question?
yeah. So my question is, I understand why we want to do the damn Jacobi because the vanilla Jacobi is terrible. But is there any reason why we also introduce the damn Gauss-Seidel here? Is it just for generality, or is there any particular practical reason that we also want to damn them?
Okay, good question. So I haven't discussed the theory of this, and I guess I may not at all. So there might be no theoretical response to your question, but the practical response is if we use a damping in our Jacob in our Gauss-Seidel method, then we can obtain faster convergence. So for example, if I don't use omega equals 1, then I forget what works best. I'm forgetting the general practice here, but I think um, slight overdamping or slight underdamping gives a really good performance in the Gauss-Seidel smoother. It's going to give us let's say if I have a V cycle that converges for omega equals 1 using the Gauss-Seidel smoother, in 10 iterations, then I might be able to improve that to 8 iterations if I tweak the value of my omega a little bit. So it gives a practical speed up. But the theory is a little bit harder. Does that answer your question?
Is he in the Purple Monster, like the theory?
The theory, no, because
I don't recall learning that in 571 and 2 as well.
okay, so it was called the SOR method previously. So it's also now covered in chapter 1. So in chapter 1, I've added a little discussion about SOR method. And so that's stands for successive over relaxation. And that one, you can show that if you use omega, I think it's around like 1.2 or something like that, then the Gauss-Seidel method converges, has an optimally fast convergence. But that's as a standalone solver, not as a smoother. So the optimal omega for smoothing, that means the optimal omega or the omega which gives you the optimally best multigrid convergence is kind of is it for certain cases it's known, but basically what you do is you just experiment and
Okay.
and we'll do that. If we have you know let's see is I guess you can answer this question, Calvin. Is there uh, a, a damping parameter in the Gauss-Seidel method that we have?
No, I don't think so.
Okay. So I guess we can't test it here, but we could put it in there and test
You can
it.
put it in very quickly, actually.
Yeah, yeah. Okay. So I won't have it for the code demo that I want to do today, but we can we can put it in there and do a code demo maybe in the future for that. Right. So we'll do omega equals 1 today. All right. What else? Yeah, I think I've addressed all that. So a nice figure will kind of explain what's going on here. So suppose I have this 4 by 4 grid and I'm going through it and updating values for my grid function. So if I'm going in the forward lexicographic direction and suppose I'm at a point 7, I want to do an update. The red indicates all the values that have been previously updated, and the unshaded are values that have yet to be updated. So if you go back and look at the formula, there were 2 point values that I updated or used the sigma plus 1 in the update. And that was this one, sigma plus 1, and here sigma plus 1. And this one, I haven't visited that point yet, so that's at sigma. And 11, that's going to be at sigma, right? Of course, 7 is the one I'm currently interested in updating. That's the so-called diagonal point. Okay. And here's I uh, equals 3, j equals 2, right? I'm at that grid point. What if I do this in reverse lexicographic ordering? So I proceed through the grid, but instead of going in the forward lexicographic direction, I proceed in the backward lexicographic direction. That just means I start counting at this upper right-hand corner and I proceed this way, right? Count 1, 2, 3, 4, 5, 6, 7, 8, etc. So in the 7th point there, that's going to correspond to I equals 2, j equals 3, right? And I'm currently trying to update point 7. Which values have already appeared and are already updated? Well, point 3 and point 6, right? The same ones that I saw over here. But of course, they have different I and j values, right? So this one is now going to be j equals 4, I equals 2, and this one is j equals 3, and I equals 3, right? So, but these points have not yet been visited, so those are at level sigma. Okay, you can see as I'm coming along here, I'm updating this point to sigma, from sigma to sigma plus 1. All right, so now you can go back into this formula and you can see, okay, yeah, I visited this point, so I'm updating. I've already visited, I'm going to use the updated value. I've visited this point, I'm using the updated value. Haven't visited those points yet because they have uh, they have a lexicographic number which is actually bigger than that, okay, than the one I'm currently at. So I can't use their updated values. They don't yet exist. Right. So the next solver that I want to talk about, or smoother, is the backward lexicographic Gauss-Seidel method. And there isn't really much to say here. The basic concept is exactly the same. And I think the picture really tells the story of what's going on. You start from the same, you start with the same procedure. You assume you have some given grid function and you want to update it at every point. You first extend it to a grid function which has homogeneous Dirichlet boundary conditions. It agrees with the function that you started with in every other way possible. It's just now you're going to add ghost cell values. And now you're going to imagine traversing the indices in the backward lexicographic ordering. You write out your equations. So this is your finite difference approximation, but you're just going to put in as placeholders the stuff that you have, right, on the non-diagonal parts. And if you've already updated it, put the updated point. If it hasn't yet been updated, put the previous value. And in the diagonal entries that correspond to I and j, put this unknown value that you want to update. And here we're going to call it alpha bij. Okay, alpha sub bij. B for backward, because even though it's at the same point, looks the same as the one you just calculated in the forward direction, it's definitely not because you're doing the updates in a different ordering. So you can solve for that guy, alpha bij, as you did before. And of course, now those points that I had updated values for appear here and here, and the non-updated values appear here and here. We are going to update. So before we move on to the next point in the next index in the backward lexicographic order, we're going to do the update. Okay, so this is used in the update. That's not the update. The update is actually this damped formula, this interpolation formula. And just keep in mind, omega equals 1 refers to the standard Gauss-Seidel without any damping. Omega equals 0 is useless and nonsensical because it simply gives me the old value that I had. So you would never do that in practice. All right. And again, the framework is the same. As soon as I get a value that's useful and updated in the backward Gauss-Seidel framework, I'm going to use it in the calculation of the next point. But remember, the next point is whatever the next point is in the lexicographic ordering that I'm using. And in this case, I'm using the backward lexicographic ordering. So now we want to do the code demo. And if you go to the GitHub repo for the course, or let's see, yeah. So I posted that in your Canvas in the Canvas notes, and it's also in the description of the YouTube videos. So if you find that link for the GitHub repo for the course, you navigate there, and I just today updated the MATLAB codes uh, section, or the MATLAB codes folder. In there, you'll see some sort of file structure which looks like this. So the one we're going to be using is the code section, which is the folder which says book version. And we're going to be using this code in 2D cell-centered, okay, 2D CC. The first thing I'm going to start with is this code in this folder called Poisson, and then we're going to go on to elliptic non-constant diffusivity code. So I have MATLAB already cracked open here. And let's see. So what should I say about this? So now you can see that same file structure is represented here. So if you go to MATLAB code, book version, 2D cell-centered Poisson, then you'll see these codes listed here. All right. The one you want to open, let's close this guy to start. The one you want to open is called Poisson 2D MG, which stands for Multigrid Cell-Centered, CC. And if I look at the top of this, the first things you'll see at the top of this code, let me resize this so that it's you can see it pretty well. So once you click on that, you'll get into the command window, and you should see the code. The editor comes up, I guess, not in the command window. This is actually the editor command window is down here, which we'll reference in a moment. In the command window, you'll see the first thing we do is do some initializations. For example, we're going to work on the domain 0101, and that's indicated by this these two lines here. And we're going to use a grid which has 1,024 grid cells in both the X and the Y directions on the finest level. All right. So the number of multigrid levels that we can use in that case is capital L equals to 10. So maybe one of you can check, is 1024, is that 2 to the 10? Let's see. 2 to the 10, I forget. Is that 1024? Yeah, it's 1024. All right, so this that's the largest L could possibly be. If we try to use L equals 11, it's going to give us an error saying that you can't use that many levels. And the reason why is because there's no way I could actually coarsen uh, the grid down to well, I'll show you. So basically, it would be saying that you'd have to have a grid which is smaller than a 1 by 1 grid, which is impossible. All right, so that's the total number of levels, and capital L represents the finest level. The size of our H on the finest levels, of course, the difference between um, you know 0 and 1, and divided by the number of levels, and L, or actually the number of grid points, 1024. And so this is 1 over 1024 basically. But I've given this H in both the X and the Y directions. And the one thing we want the code to do is make sure that the grid spacing in the X and the Y directions are the same. Okay. And that's done here, but we're not going to talk too much about that point. Now I want to initialize some of the parameters used in my multigrid solver. The first one is, what kind of method do you want to use? And we want to use a V-cycle method to start. So that's indicated by choosing P equals 1. That's standard, and that's what's reflected in the book and previous courses. So P equals 1 represents standard V cycle. If we want to choose the standard W cycle, we're going to choose P equals 2, etc. If we want to reflect what we've the theory that we had previously from chapter 5, which is now chapter 6, incidentally, we have to choose P equals an even number. So that could be 2, 4, 6, etc. So P equals 2 works just fine. M1, that's the number of pre-smoothing steps, and M2 is the number of post-smoothing steps, and omega is precisely the damping parameter that we choose for the damp Jacobi method, or the Richardson smoother. Right. So basically, I didn't discuss this point, but this was touched upon in an earlier section where we said, in a certain way of looking at it, if you do some certain manipulations, the thing that we call the quasi-Jacobi method works out to be exactly, or damp quasi-Jacobi works out to be the same as the Richardson's method. I've added a little bit more detail on that in chapter 7/8. So when you read that, you'll understand what I'm talking about. This is just some checking to make sure our multigrid mesh is set up correctly. For example, it checks to make sure that this L is not too large for the number of grid points that we've chosen, etc. Right? So after we do those checks, then this puts all of our variables, parameters that we've just set, into what's called a structure in MATLAB. This allows us to pass this information to many parts of the code very easily without making a global parameter. This allows easy passage. So what we do in this code is something that's really only possible for teaching codes, and that is we put in the exact solution that we want to compute. And the reason why we do this is because, well, we want to pretend that we're actually doing real work here and what I mean is, we want to pretend we don't know the true solution, but actually we're putting it in the solver. The reason why we might want to do this is because we want to compare what the code is going to give an output as an exact solution versus what we know to be the exact solution. The way this works is basically we're going to put in an exact solution. In this case, it's a it's a it's a solution that has homogeneous or will satisfy the homogeneous Dirichlet boundary conditions at the discrete level. And what we do is we're going to manufacture the forcing vector so that this is exactly the true solution. And the way you do that is you simply set f to be equal to the finite difference operator acting on that thing you just proclaimed as the exact solution. And that's doable because, well, we know what the finite difference operator should be. In this case, it's just the standard Poisson equation. If we open that piece of code, it's the 5-point stencil for the standard Poisson equation. Now, what makes the cell-centered finite difference method nice and easy to use is that we can simply enforce the values of the ghost cells at the ghost cells, and then we can call this finite difference operator, and we don't have to change our stencil near the boundaries. And so that's one of the winning concepts of the cell-centered finite difference method is I can always set up my ghost cells to satisfy the correct boundary conditions so that I don't have to modify the stencil at all. And so this is what we call a vectorized application of the standard 5-point stencil. There are exactly 5 points in this, but it's vectorized, so it looks a little bit mysterious in how it's calculated. And so you might want to, before you try to code up a vector formulation of the 5-point stencil, you might want to put it in a do loop or a for loop and do it that way first. It just turns out that that is not quite as efficient as as putting it or vectorizing that computation. And it looks a lot cleaner if I vectorize it. So let's go back here to our calling code. So this code here is not a function in MATLAB. It's a what's called a script. And so this guy is what's going to call all the other functions and codes, which is going to do call the solver and spit things out. Okay, so we were here, we calculated the F so that we had the exact solution, and now we come to the multigrid solver, okay? So this piece of code here, what we're going to do, what this says is these are all the input values for a MATLAB function, and these are, of course, the output values. Tick and talk, that's simply a way of monitoring how fast the code runs or how long it takes in order for us to compute a solution. We're going to pass U. So what is U? U should be our initial guess at the solution. So let's go up here and see what did we set for U. For U, we just set it to be some random set of numbers. In fact, this case, I think this is just going to be a uniformly distributed set of random numbers between 0 and 1, and we're going to subtract 0.5. So basically, it's just a bunch of crazy noise that we're going to use in this calculation. So that's what we're putting in as the initial guess. It's about as bad as you could get for an initial guess. Of course, we know the true solution. You could put in the true solution as your initial guess, but that's really cheating because what we want to do here is test how well our solver works. Here's F. F is our forcing function. HL is the size of our mesh spacing on the finest level. These are our mesh parameters in the thing called the MG param structure. And we're going to pass the true solution to the multigrid solver because we're going to use that to compute the error. And the only way you can compute the error is if you know the exact solution. So before I get on to the nitty-gritty of what's inside this multigrid solver, let's just run it and see how it goes. I will say that there's a few other steps in this code, but we're going to ignore those for the most part. Those are just the plotting of the true solution once it's gotten. We make a surface plot of that, and then plotting of the error. Okay, so basically below this line is simply plotting, and I'm going to ignore that because that's not multigrid, that's just window dressing, I guess. All right, so how do I run this code? The code is already set up to run. So if I have this editor open, you'll see that in editor mode or in the editor tab, I have this run button. And what I can do is just click that button and it's going to run that code. It's going to give us a couple of different outputs. So in figure 1, I get the true solution. And that is just that exponential of the sine function that we exhibited earlier, that weird looking function. Notice that to the eyeball norm, it satisfies homogeneous Dirichlet boundary conditions on the edges of the square. We're solving this on a square. And it has an up, couple up bumps and a couple down bumps. And well, we'll just take it for a fact that that is the solution. This is the filled contour plot of that solution. You can rotate it as a surface plot or view it in plain view as a kind of filled contour plot. Okay, got a chat here. Yeah, someone says it looks like, Calvin says it looks like the binary neutron star system. Yeah, I guess like they're evolving around each other. Yeah, I guess it does. All right, now the second plot, plot 2, is the error. In fact, it's a bunch of different errors. In the blue circles, um, it's showing, let's see, I can blow this up a little bit, and that might be, hope that appears larger to you. But the blue circles are the norm. It's just the Euclidean norm between the exact solution and the computed solution at the finest level. And we're seeing that is decreasing. It's actually decreasing fairly rapidly. In fact, what we can show is that we have a contraction, a computational contraction rate of the error in whatever norm we're computing it of about 8 times 10 to the minus 2, right? So that means every time we do a multigrid iteration, we're decreasing the error by that amount, by this amount gamma. So every time I do an iteration, it's basically reducing the error by this fixed amount. And it's completely it's mostly more or less functionally independent of the number of levels, capital L is the number of levels that we have. So we could increase the number of grid points by doubling that 1024 to give us 11 total levels. This number is basically going to stay the same. So that's called the contraction rate. All right. What is this? What are these points in red? So the points in red are what we call, let's see, what did I call that? It's what it is the difference between, it's kind of maybe too small to see here, but you could see it if you run the code. It's the difference between the two successive iterates in my multigrid method. And the idea is as you converge, the difference between any two successive iterates should become smaller and smaller. In fact, you can see it tracks basically with exactly the same uh, log linear slope as the error function. And so this gives us a good indicator of how fast we're converging. The black diamonds. What are the black diamonds? Black diamond is a norm of the residual vector. The norm of the residual vector is something that's very easy to calculate for us because residual is just remember, you can always compute a residual if you have an approximation. You may not know what the error is, but you can always calculate the residual by doing in matrix vector form f minus a times u, where u is your guessed solution or your approximate solution. So this also is decreasing at the same rate, log linear rate, as the error and this red thing, and it's escaping me now what I called that red thing before. Um, but any one of these two in the black diamonds or the red squares, either of those two measures could be used as a pretty good approximation or an indicator of what your true error is because they're both seem to be decreasing at the same rate.
Is
All
it
right.
like Cauchy difference or like stepwise?
Well, yeah, let's see. Um,
I think it's
yeah,
measured.
it's kind of
Measured.
like the Cauchy difference, kind of like the Cauchy difference. But I had a name for it, and I now I'm just blanking on it.
I have another quick question.
Sure, go.
I remember you talked about it before, but I actually don't understand at that time. So I think you say something like error can be reduced like indefinitely, but residual cannot. Is it?
So let's see. So as long as you're reducing the error, you're reducing the residual. They go hand in hand. Um, but basically, let's first talk about numerical error. So or round off error. Eventually, you're going to get to such a small error if we demand that the stopping tolerance is like 10 to the minus 13 or 14, we can't reduce the error anymore. That's simply because round off error starts to dominate our calculations. And we may have to increase our precision on our floating point calculations from, let's say, double precision to quadruple precision. But as long as the error is going down, or as long as the residual is going down, or that, let me say it correctly. As long as the residual is going down, the error should be going down, and vice versa. They kind of, but if one of them starts to bog down and doesn't reduce, then the other one is going to probably do the same. So let's test that out. Let's try read. Let's try changing our tolerance. Right now we're stopping at a tolerance of 10 to the minus 10. So I don't know. Let's try 10 to the minus 14 and see if that can work. I have a feeling it's maybe going to start to bog down, and maybe it won't converge to that small of a tolerance. Actually, let's sneak up on this. Let's try 10 to the minus 12 first. Okay, 10 to the minus 12, we're still okay. We're getting a log linear convergence, right? A geometric convergence. Okay, let's push the envelope a little bit. 10 to the minus 13, still okay, all right? But we're seeing, I don't know, maybe actually it looks like the rate is increasing down there. That's puzzling. Okay, somewhere along the line, we're going to break things. Okay, we just broke it. There we go. Basically, you're going to get a new what's called a numerical saturation at some point. You simply can't do any better. If you try to push it, what did we try? 10 to the minus 14. I'm glad we didn't try that at first because you can see you can make it so far, but after some tolerance, you're just in the noise. You're in the numerical you're in the round off error noise. So it's kind of art to figure out how much you can push these codes. So we're not going to push it too far. We're going to say, 10 to the minus 9 is even good. So that's already a pretty small tolerance. Okay. Let's see. What do you guys want to change? What should we change first to test our multi-grid convergence? Let's test a couple of these guys, right? So one thing you can play around with is you can do some tests and run a bunch of tests, leave all the other parameters the same, and maybe just change omega. So let's try changing that first. So let's go back and check. So we 8.62 times 10 to the minus 2. That's a pretty good contraction rate for when we choose omega equals 2/3. Let's back that off and try 0.5. Okay, so we choose that. Do we expect to get a faster convergence rate or a slower convergence rate? So we want to see faster convergence means that gamma parameter is going to be smaller. Slower convergence rate means the gamma parameter is going to be bigger. Um, so I think based on my experience, it should be slower, and it is. So this parameter has gotten bigger. It's still quite good. It's 3.9 times 10 to the minus 1. That's a pretty good convergence rate. Now let's see, what are we using right now for smoothing? I think smoothing, we are currently using, I've got to check, let's see, let's drill into, well, before I get onto that, let's try making that parameter slightly bigger. So we tried 0.7, it got worse, or 0.5, it got worse. Let's try 0.7. So two-thirds, that's 0.66. That gives us 8 point something times 10 to the minus 2. Let's see if we get a smaller contraction factor, meaning faster convergence if we up that omega a little bit. Yeah, we did. So taking it a little bit larger gives us a faster contraction by a small amount, 7.1 times 10 to the minus 2. And it looks like it's converging in 8 iterations. So that's definitely an improvement. How far can we push it? We go up to, let's go 7.5. Let's see if this improves things. Yeah, still getting better. So let's push it further. And if we're using Jacobi, which I believe is what we're going to use, or what we've been using here, it should start to bog down and start to fail around this, or start to get worse around 0.8. What was the last one? Because anybody remember? Was it 4 times 10 to the minus 2?
7, I think.
Okay, so now I have to go back and check. Okay, so 7, 5. So whenever he had 8, let's keep track here. We had 0.8. That was a contraction factor of 5.3 times 10 to the minus 2. And if we, so that was 8, right? So 0.75. What does that give us? 5.9. Okay, so it's still getting better. Um, hopefully this trend doesn't continue, or else I don't know what's going on. Should start to get worse now. Yep, now it's starting to get worse. Okay, good. So if I try to push that damping parameter up too much, we start to get a degradation again. So you could do a plot. If I did a plot, then there'd be some optimal value that you could find for omega. And it must be somewhere around 7, I don't know, 7.5, 7.3, something like that. So this one is 7 times 10 to the minus 2. So far, 0.8 is the best. So maybe 0.81, I don't know, something like that. So you can play around with this and see, what value gives me the best contraction factor. Of course, if I do more smoothing, I do expect to get a faster convergence rate. But remember, more smoothing comes with more cost. That's an added cost. So 4.6 times 10 to the minus 2, that's definitely better. More smoothing gives me a faster contraction, but doing more smoothing comes with a pretty significantly greater cost. So I don't want to do too much smoothing because it's pretty expensive. I want to do just enough that I get convergence. So how would I test this one? Well, I could test this one with the total speed. I could do a fairly careful speed test because I'm keeping track of how long it takes to do these computations, and I can see how long each change is taking. So if I fix one parameter and then I start messing around with the number of smoothing pre and post smoothing steps that I do, then that should tell me, if I keep track carefully of the elapsed time, what's giving me the best bang for my buck. So if I do 4 at these, every other parameter being the same, if I'm doing 4, it's costing me 0.54 seconds. So let's see what happens if I change back to 3. I'm not gonna get quite as fast a contraction factor, but 3 is a lot cheaper than 4 in terms of floating point operations. Yeah, so I get a slightly faster convergence. Instead of 0.54, it's 0.52, right? So I actually go up. I actually have a gamma, which is slightly bigger. So that means the convergence rate is not as fast per per step and per step in K. However, um, my the total elapsed time is smaller because 3 smoothing steps is a lot cheaper than 4 smoothing steps. Okay, so let's try switching from P cycle 1 to P cycle 2. So that means we're going from a V cycle to a W cycle. That also ideally should speed up the convergence. Um, so let's see what happens in this case. So now we're no longer doing a V cycle, we're going to do a W cycle. Okay, so let's see, zero point 0.7. I forget what the contraction factor was. I'm not sure. It doesn't look like it's necessarily faster convergence than the V cycle. But again, I didn't keep track of it. Um, let's see what happens if we go from P equals 2 to P equals 4. That's another type of W cycle where P is even. It's a more complicated looking diagram, but it should work as well. Let's see what we get. It's really expensive to do 4 apparently because I'm not getting any output. That's something we'll need to check that it's not broken. There we go. That's taking an awful long time. I guess the reason why is because when I use P equals 4, that's a lot of recursion on 10 total levels. So error is coming down. So it looks like it's coming down pretty well. So it's a contraction factor in the neighborhood of, oh, that one is not as great. I'm gonna stop this one because I just don't want to wait so long. So I'm gonna stick with something that converges in my lifetime. Okay. I'm a little bit surprised by that. So I might need to dive in there and make sure there's not some sort of strange computational error going on, which is costing me so much time. But in any case, let's have a look in this multigrid solver, see what that is comprised of. So let's see, where is that guy at? Multigrid solver. Here we go. All right, multigrid solver. We already talked about the inputs and the outputs for that. Right. So let's see. Now I have to remind myself how this works. We're going to enter a loop, right? That's our main K loop, and checking to see if uh, um, we're getting convergence. This is the main multigrid operator. So this is the MG operator that I think in the book we just called this MG. And what goes in here is the level, and we start out at the finest level. So we start out with capital L, and these other parameters. And then basically this thing calls itself recursively, right? According to our standard multigrid algorithm. After it calls itself, it goes all the way down and then all the way back up, then that's one iteration. From that one iteration, we can calculate the error values that we have, right? The various error calculations. So we know the true solution that was passed to the thing through uexact. What else do we know? We can calculate the residual. We can also calculate the difference between the two successive um, iterations. Okay, the whose name I what did I call it? Oh, yes, the correction value. So that's called the correction value. This guy right here. When I'm calculating the norm of the difference between two successive iterations, that's called the correction value. Okay, so this is just multi-grid algorithm is calling itself at the top level and then finishing. and then giving us the various outputs. And then what is this guy calling? The main thing that this is calling is the multigrid operator, MG operator. So that's the thing we want to kind of crack open. This is a function which calls itself. So in MATLAB, this is what's called a recursive function. What are we using for smoothing? Looks like we're using damp Jacobi smoother for smoothing. This isn't actually damp Jacobi. This is this is actually a Richardson's method, or I would call this a damped quasi-Jacobi. All right. So, but don't worry too much about that. Now we have alternatives to this. We don't have to use the damped Jacobi method. This one doesn't work, the smoothing by Jacobi, so we're going to remove that at some point. We could use Gauss-Seidel as the smoother. So I think that's what I want to do now. I want to use the Gauss-Seidel smoother. We do have to remove that space there. For our pre-smoothing. But to symmetrize the method, what we're going to do for our post-smoothing is we're going to use the Gauss-Seidel smoothing with, instead of running it in the forward direction, we're going to run it in the backward direction. So I think that's the change I want to do. So let's comment out that bad boy there. And we're going to use Gauss-Seidel, but with the backward direction smoothing. Okay, so this code and how this works is laid out in the smooth Gauss-Seidel, and that's this function here. I'm not gonna go into what that function is or does, but this is Gauss-Seidel, and we already talked about Gauss-Seidel. This is actually the quasi Gauss-Seidel. It's not the standard Gauss-Seidel. It's the quasi Gauss-Seidel. And this one is applied with no damping, but you can add damping to this one fairly easily. Um, in this function, we have the option of running this either in the forward direction and or in the backward direction. All right, so we're going to run it in the forward direction in the pre-smoothing setting, and we run it in the backward direction to symmetrize everything when we do post-smoothing. And the computation for that is not too difficult. It's fairly simple, and it's here. Basically, once I update a value, I'm going to immediately use it again in the updating process. Okay, so let's go back out here. Let's make sure I've commented out everything. So now we're going to use backward Gauss-Seidel smoother for the post smoother. And I've commented out the damp Jacobi. And okay, so the way this code works right now, it doesn't have a damping parameter. I think we'll add a damping parameter because I've described that in the code or in the book. So let's see how well this guy runs. Now let's go back out here. We're going to rerun this code. I made a modification to multigrid operator by commenting that guy out and choosing this instead. And now let's make sure our other parameters are making sense. Let's go back to the single V cycle. And let's go back to a case where I wrote something down. So, all right. So oh, yeah, that's not going to matter anymore, right? Because there is no omega. So this is a case we've studied before. This parameter is not going to be used in Gauss-Seidel smoother. So let's see, how does the Gauss-Seidel smoother compare to the damp Jacobi smoother or damp quasi-Jacobi smoother whenever the parameter was 0.8 for the damp Jacobi. So I have that written down. Of course, for this guy, it doesn't matter what the parameter is. So let's just run that. And I think all other the parameters are the same. Yeah, look at how much better that is. So for Gauss-Seidel smoother, using 3 post-smoothing steps and 3 pre-smoothing steps, V cycle, our contraction factor is now 2.6 times 10 to the minus 2. And for the damp Jacobi method, it was 5.3 times 10 to the minus 2. That was the best performance that we could get. And so Gauss-Seidel, without any damping, is basically 2 times faster, or it has a contraction rate which is 2 times smaller. So that leads to a much faster convergence. Now, practically, if we add an omega parameter, getting back to Calvin's question of earlier, if I add a damping parameter to my Gauss-Seidel smoother, I can bring this contraction factor down even more. I might be able to make it as small as 1 times 10 to the minus 2. So we don't have a theory for why that is so, because that is a bit complicated, but you can do these practical computations to see how this works. Um, so that's the end of my code demo there. I want to go back to the structure of how the code is set up. I mean, we might do another if you guys are really interested in seeing more code demo. I can add and I can add a class after the spring break where we go into these guys. Now, so we discussed Poisson. We also have a code directory here for the non-constant diffusivity elliptic problem, and where you can change the boundary conditions and change a lot of things. And so that is contained in this code here. This code here, elliptic constant diffusion, I guess that one is this one, but um, without the possibility that so this one is just constant diffusivity, I believe, although I haven't messed around with that lately. This one is, I think, the most interesting case, and this one delves into some of the discussion we had about the smoothing with the Gauss-Seidel method and the Jacobi method for the case where you have non-constant diffusivity. So I'll let you guys play around with that. Again, the main calling routine here is going to be this guy, elliptic 2D MG variable density or diffusivity. This guy right here is going to be your main calling routine. So you can go, if you want, go ahead and check that out. The main difference between what we had previously and what this guy is going to represent is that this one is going to allow you to do non-constant diffusivity, and you can set up more complicated problems in there. So go check that out if you're interested. All right, that's where I'm going to end the lecture today. Thank you for your patience, and you can turn your camera back on.